All right, we're going to go over some problems from the 4-9 Solving Polynomial Inequalities worksheet. So solving polynomial inequalities is a lot like solving polynomial equations, but way more fun. So right here we have a regular quadratic. If this was an equation, if this was equal 0, or if we wanted to represent this polynomial with a graph, it's second degree, it's a quadratic, it would make a parabola. Right? And a parabola that opens upward because of the positive leading coefficient. However, if it were an equation, what we'd be looking for is the two spots where it is equal to 0. If this is our x-axis, we want to know where it crosses the x-axis, where the y values would be equal to 0. However, since we are not looking for when it's equal to 0, but when it is less than 0, we want to know what part of the graph lies below the x-axis, what part is less than 0. So we're actually looking to figure out what section of the graph we're looking at down here. We want to know what numbers these are. What are these two numbers that this bottom part of the graph is in between? And we're going to figure out those numbers the same way we would solve it if it was an equation. So we're going to go ahead and factor this. We need two numbers that multiply to 2 and add to 3. So that is 1 and 2. So we have m plus 1 times m plus 2 is less than 0. And well, just kind of like the zero product property, we're going to pretend this is sort of an equation. So we can find these boundary values by just sort of solving for them. So this one would tell us one of our values is -1, and one of our values is -2. So since -2 would be on the left of -1, we'll say it's there and there. Now, our graph is going to be below 0, less than 0, between -2 and -1. So we can write that two different ways. We can say that -2 is less than m, which is less than -1. So m has to be between those two numbers. Or we could write it as an interval and say our solution is between this should be an open parenthesis because we're not including -2 and -1. It's between these two values, not including them. All right. Next problem here. So before I get into what we were doing before, I need to make one side equal to 0. So I'm going to move some things around. I'm going to subtract 2p, and I'm going to subtract 4. That'll give me 0 on this side, and subtract 4. So we end up with p squared minus 3p minus 4 is greater than or equal to 0. All right. Hopefully you'll notice this also could be represented by a parabola. So let's go ahead and sketch a parabola. Again, and if it was an equation, we'd be looking for these values. Different from the last one, we're not looking for when it's less than 0, when it's below the x-axis. We're actually looking for when it's greater than 0 or equal, so we're including these. We're looking for when it's above the x-axis. So we want to know these sections of the graph here, when it's above the axis. So our solution is actually going to be two separate intervals. It's going to be from here to infinity, right? Because it keeps being above the x-axis, or from -infinity all the way up to here. Here's where it goes below. So we're going to have two intervals for our solutions. All right, to find these boundary values, I'm just going to pretend it's an equation. I'm going to pretend this is just equal. But all right, let's go ahead and factor it. We need two numbers that multiply to -4 and add to -3. We have -4 times +1. That would work. So our factors are going to be p minus 4, and p plus 1. And again, for our purposes right now, we're solving for these boundary values. We're just going to pretend it's an equation. So p minus 4 equals 0, p plus 1 equals 0. One of our solutions is p equals 4 and p equals negative 1. So this number on the left side would have to be the negative 1. And this number on the right side would have to be 4. So our first interval, we could write it in interval notation, would be from negative infinity all the way up to negative 1. And in this case, because of the or equal to, we are including negative 1. And then our other interval, so we include, this is the union, we'd include this other set as part of our solution. We start at 4, and we go all the way up to infinity. We always use open parentheses for infinity. So this is one way to represent our solution using interval notation. Or we could say that p has to be less than or equal to negative 1. That takes care of this side. Or p is greater than or equal to 4. So we can use it as interval notation or this sort of set builder or inequality notation. Either way. All right. Now, number 18. Again, doesn't say equals 0, so I'm going to first start off with some algebra. Distribute this. And I'm going to subtract the 2 over. So we end up with 9r squared minus 9r minus 2 greater than 0. All right. Again, this is a quadratic. It's going to be a parabola. Again, positive, so it's opening upward. We're not looking for these solutions here in particular. Actually, I probably should represent them as open circles since we're not including equal to 0. So pretend those are open circles for this problem. We want to know when it's greater than 0. So we want to know when it's above the axis. So we're looking at this region again. When it's above 0, not below 0. It's greater than 0. And we need to factor this. I'm going to show one way to factor. So this is the A, this is the A, this is A times C, and this is B. Okay. So A times C is negative 18. A is 9, A is 9, B is negative 9. All right, I still need two numbers that multiply to the top and add to the bottom. So multiply to be negative 18 and add to be negative 9. Kind of going through that. If I have to multiply and get a negative, I know I need a negative number and a positive number. 18 doesn't really have that many options, right? You might be tempted to think 3 and 6 because that would get us 9, but if one of these is negative and one of these is positive, it doesn't seem to work. This one actually seems like there's not a clean factoring, which makes me wonder if I copied the problem down wrong. So I did. Okay, so this is negative 2, which means that I would have to add 2, which makes this a plus, which changes this to positive 18. Fixes the whole problem. All right, multiply to a positive and adds to a negative. So we need two negative numbers, and it is 3 and 6. Okay, ignore that little mistake, but yeah, they happen. Okay, so now for this process, I need to factor a common factor between these numbers. So I have 9 over -3. They're both divisible by 3. So I'm going to get 3 and -1, which gives me my first factor as 3x minus 1. And then I have this other factor. I have 9 and -6. Again, those are both divisible by 3, which gives me a 3 and a -2. So my other factor is 3x minus 2. Okay. If you don't know this factoring, that's okay. However, you can get to the factored form here. All right, go ahead and quickly solve these. This one is going to give me a solution of 1/3. And this one is going to give me a solution of 2/3. So our two boundary values in this case are 1/3 and 2/3. So 1/3 would be on the left, 2/3 would be on the right. Again, negative infinity would be this way, positive infinity would be this way. We can write our solution either using interval notation or with the inequality symbols. Doesn't really matter. I'm just going to, for this case, just write it once. R is going to be less than 1/3, meaning we're not including that point, so it's going to be less. Or R has to be greater than 2/3. Again, we're not including the point, so no or equal to. Anything bigger is good. Again, you could write that using interval notation as well. We will do both. Okay, last problem. I think this one's slightly easier than the previous one. We will see. Yeah. So again, I need to do a little algebra first. To get that to be one side to be 0. Okay. So again, positive leading coefficient here. So I'm talking about a parabola opening upward because it's x squared. Squared always makes a parabola. Or equal to, so we are going to include our boundary values this time, and we want to know when it's less than 0. So we are looking for the region below the x-axis. We're looking for this part. So we need to know it's between these numbers, and we'll factor it. Two numbers that multiply to 4, add to -4. It's going to be two negatives, -2 and -2. And this is interesting. This will be x minus 2 times x minus 2 is less than or equal to 0. Well, we're looking for the boundary values, so we're going to pretend it's an equation for this part, right? These are going to give us the same solution. They're going to say x equals 2. They're both going to give us that solution. So that means that both of these numbers are 2. What it actually means is this. It means that we have our x-axis, and this parabola does not dip all the way below it. What it does is it comes down, it touches it at 2, and then it goes back up. So it never actually goes below the x-axis. It's equal to, but it never actually goes below it. So our solution to this inequality is actually just a single number, only 2. X equals 2. That is the only spot where our parabola is either at, equal to, the line below 0, or below it. So in this case, it never gets below it, but it does get equal to.